Hey students, welcome to lecture number 12 of Linear Algebra 1. So the last two times we talked about bases of subspaces, and then in the last lecture we talked about coordinates. So let me recall a little bit. So if I have a subspace U, so a subset of Rn satisfying these three conditions, then we defined what it means for vectors to form a basis. So we had this notation here last time, that we write a basis like a tuple like this. And this here was a basis if these elements, b1 up to bm, they span the space U. So this means I can write every element in U as a linear combination of these vectors. And the second condition was that they are linearly independent. And from this it follows that every element in U can be written uniquely in terms of these elements. So if I have an element in U, so let's say I have x in U, then I can find unique lambdas. So this symbol here means I can find unique lambdas, lambda 1 up to lambda m, such that x can be written as lambda 1 times the first basis vector plus lambda m times bm. And in this case here, if this basis has m elements, then the dimension of the subspace is m. And these numbers, which are unique, if we start with some element in U, these are called the coordinates of this element x. And then we had this notation that the coordinate vector of this element x with respect to the spaces here is just the vector of these m coefficients, lambda 1 to lambda m. So this here is an element in Rm. Even though this element x here, so this is an element in U, and U is a subspace of Rn, but the coordinate vector is in this space here, where the dimension of the space is given by the dimension of the subspace U. And what we want to do today is talk about a special type of basis, which are called orthonormal basis. And so this will be a special type of basis which satisfies a certain condition. Namely, the condition will be that these vectors b1 up to bm are pairwise orthogonal to each other. So meaning the dot product of them, if I take two of these elements, then the dot product is 0. And they also have a length 1. So this is the normal here. And then at the end we will talk about the so-called Gram-Schmidt algorithm or Gram-Schmidt process, which will be an algorithm to construct an orthonormal basis given an arbitrary basis like this here. And we will also see that this has nice properties. So for example here, if I have an arbitrary basis b and I give some element x, then to calculate these coordinates you need to solve a linear equation to get this coordinate vector. But we will see if the basis is an orthonormal basis, then there's an explicit easy formula for these coordinates, which is basically just given by the dot product. But before we introduce this, let us recall some notations. So recall. I mean these notations of orthogonal and so on. So first, if I have two vectors, x1, so an element in Rn, and this vector y is also an element in Rn, then the dot product we denote it by x, and then this thick circle here, x times y, this is just given by x1 times y1 plus x2 times y2 and so on up to xn yn. And then we said that two vectors are orthogonal This means that the dot product of these two is 0. And if n is 2, this just meant that, for example, if I have the vector x here and the vector y, then orthogonal means that they are perpendicular to each other, meaning that this angle here is 90 degrees. And also in R3, if I have two vectors in R3, then orthogonal means that they are perpendicular to each other. And then we also defined the norm of a vector. So we denoted this with these two lines, and this was given by the square root of the dot product of x with itself. So in other words, this here is just x1 squared plus xn squared, and then we take the square root. And this is just in R2 and R3, this is just the length of a vector. Because you see by using the Pythagoras theorem that you get this formula if you want to calculate the lengths of these vectors. So this is nothing new. And now some properties of these, which follows from the definition. So one property is that if I take the norm of lambda times x, where lambda is as always some real number, then I can put this lambda outside. So this is just lambda times the norm of x. And here at this point, this here is the absolute value of lambda. So if lambda is negative, then we just take the minus lambda here. Okay, so in other words, if I have a vector like this and I multiply it with 2, then of course the statement is that the length of this new vector is 2 times this vector. And if I multiply a vector by, let's say, -2, then I change the direction, but I also increase the length by 2. So then this -2 here becomes a +2. So the statement then is that the length of the new vector, which now shows in the other direction, but the length of this, so the norm, is just 2 times the norm of the vector before. And the second statement is an inequality. So if I take the dot product of x and y and take the absolute value, then the statement is that this is smaller as the product of the norms of these two vectors. So when we introduced norms, I also made a comment that actually here I could multiply with the cosine of the, I mean if we are in the case when n is 2 or n is 3, then this here I have an equality here, where here I have the cosine of phi, where phi is the angle between these two vectors, and therefore the cosine of a number is between -1 and 1. So here we see that if I forget this factor, in general one has this formula here that the absolute value of the dot product of two vectors is smaller or equal than the product. So this here is just the product of two real numbers of the norms of x and y. And this is called the Koshi-Schwarz inequality. And also, if x and y are linearly dependent, meaning, what does it mean if two vectors are linearly dependent? If I just have two vectors, then linearly dependent just means that one of them is a multiple of the other, meaning that the angle between them is 0. In this case, this cosine is 1, and therefore here this equality is exactly the so here in general it's smaller or equal, but we have equal exactly in the case if x and y are linearly dependent. But actually this equation is will not be so important for us today, but I just wanted to mention it as a comment that you heard of this property, which is called the Cauchy-Schwarz inequality. And the third property, which somehow makes sense, is that if I take the sum of two vectors and then take the norm, then this is smaller as the sum of the norms of x and y. So in R2 and R3 this should be clear, because if I have a vector x and I would add a vector y, then this vector here would be x plus y. And of course the length of this vector here is smaller than the length of this plus the length of this one here. And because of this picture here, this is also called the triangle inequality. Okay, so this was just a recall of these old definitions we had, and now we want to define a new notation using these. And so this is definition 12.1, and the first notation is the following: if I have a vector u in Rn, then this is called the unit vector if it has a norm 1. So if I just have length 1. So in R2 the unit vectors are exactly those vectors which are on the unit circle. And if I have an arbitrary vector which is not the zero vector, then I can always change the length of this vector to make it a unit vector. And the notation we use here is this u hat. And what we need to do to make it to length 1 is just we divide by the norm. So if u is not 0, then the norm of u is not 0, and therefore I can multiply this vector u with this scalar here, this 1 over the norm of u. And then after this, this u hat here is a unit vector. Because what is the norm of u hat? Well, the norm of u hat, by definition, u hat is 1 over the norm of u times u. And by this property we saw before, if I have a scalar times a vector, then I can put the scalar in front. So this here is always positive, so I don't need to take the absolute value. And here I just have the norm of u, and therefore this is a 1. And therefore this is a unit vector. And now the important new notation here is the notation of being orthonormal. So there are two ingredients in this word here, this ortho for orthogonal and this normal. So what this means is if I have vectors, let's say I have L vectors u1 up to ul, which are vectors in Rn, then these vectors are called orthonormal if they are pairwise orthogonal and all of them has norm 1. So this one can put into one formula stating that the dot product of ui with uj, so I take two of these and take the dot product, so this is either 1 or 0. It is 1 if this I equals j, so this just means that for each of these ui dot product ui, this is 1. So in other words, this just means that the norm of this is just 1, because the norm of this is given by the square root of the dot product of this with itself. So this condition here just means that all of them are unit vectors. And this condition here, if I take two different vectors out of these L vectors, then the dot product is 0. And this just means that they are orthogonal. Okay, so orthonormal means basically two things. One thing, they are pairwise orthogonal, and they all have norm 1. And then our main object today is the so-called orthonormal basis. And, well, the definition is maybe not clear. A basis is called orthonormal if the vectors in this basis are orthonormal, with the definition as before. So meaning I have a basis of a subspace U, meaning they span the space and they are linearly independent. And they are also orthogonal to each other, and they all are unit vectors. So what is one example for this? So for example, if I take U to be the whole space, what is a basis we can always write down for Rn? It's this standard basis where we have this vector e1 up to en. So this here is a vector 1, 0, 0, 0, and this here is a vector 0, 0, 0, 1. And of course all of them are unit vectors because the norm of each of them is 1, but they are also orthogonal. So if I take the dot product of this with this, for example, then clearly the dot product is 0. So this is an example of an orthonormal basis, which I will just write O and B in the following. Okay, but the goal is today to construct orthogonal basis in general by starting with an arbitrary basis. So, but first, this proposition here. And so the first statement here is that if I have vectors which are orthonormal, then they are automatically linearly independent. So this is a nice property, because usually to check if vectors are linearly independent, you always would write them into a matrix and then try to solve a linear equation. But if you can show that they are orthonormal, so you just check if they are orthogonal to each other and have length 1, then you can automatically deduce that they are already linearly independent. And you will see that the proof is actually quite easy for this. And then another nice fact about orthonormal basis is the following. If I have a basis which is an orthonormal basis of some subspace V, and now I take an element of this subspace, then as I said in the introduction, we can define what we mean by this coordinate vector. So the coordinate vector of u with respect to the basis B tells us how we can write u as a linear combination in this basis here. And the statement is that the entry of this coordinate vector, so this is what I called lambda 1 up to lambda m, these are just given by the dot product of this element with the corresponding basis vector. So the coordinate vector we can write down without solving any linear equation. So because this is a coordinate vector, this just means that u is this linear combination of this basis here. So here this is what we usually call lambda I. And then another nice thing about orthonormal basis is that if I have an orthonormal basis, then if I consider the dot product of two elements in my subspace V, then this is the same as the dot product of the corresponding coordinate vectors. So in particular this means if the coordinate vectors of two elements are orthogonal to each other, then also the elements in the subspace are orthogonal to each other. Okay, so let's prove this nice proposition here. So number 1, we want to show that if we have vectors which are orthonormal, then they are automatically linearly independent. And what we want to show for linearly independence is that we consider a linear combination of these vectors. So we assume we have a linear combination of them which is 0, and what we want to show now is that these lambdas are all 0. And then this is the definition of these vectors being linearly independent. And now what we can use is that these vectors here are orthonormal. So what we can do is for all j between 1 and m, we can now multiply this equation on both sides with one of these vj's. And by multiplying I mean taking the dot product. So we can take vj dot product of this thing here and also take the dot product on the right hand side. Well, on the right hand side, because I mean this here is just a 0 vector and the dot product of the 0 vector with something is again just a 0 vector. But here on the left hand side, so we learned that the dot product satisfies the property that I can just, so I can multiply this with this plus this with this and so on. So this here we learned is the same as lambda 1 Vj dot product V1 plus lambda 2 Vj dot product V2, and so on up to lambda m Vj dot product Vm equals, oh well, it's still equals 0 here. And now we can use that these vectors are orthonormal. Orthonormal means that they are pairwise orthogonal. So, for example, if j is not 1, then this expression here is 0, because then Vj and the dot product with V1 is 0. And here also this would be 0. But just at one point we will get the dot product of Vj with Vj, and in this case the dot product is 1. So the only remaining part here is lambda j times Vj dot product Vj, which is 1. So here the result is just that this is lambda j. And therefore lambda j equals 0. So this here is now the number 0, and this is the vector 0. But here vector times dot product with the vector gives number 0. So here we see that for all j, lambda j equals 0. And therefore these vectors are linearly independent. Okay, and now the second statement. We want to show that the coordinate vector is given by this. So if I have an element, so I have an element u in V, and we want to show that u can be written like this. And what we know is that we have an orthonormal basis. So the first statement is that we can write u as a linear combination, lambda 1 V1 up to Vm, lambda m times Vm. And now if we again multiply now both sides with some Vj, so for all j between m and 1, I can again multiply both sides here, taking the dot product. Then we see on the left hand side we have Vj dot product u, and on the right hand side with the same argument as before, because the Vj's are orthonormal, everything cancels out except for the term here at the j's position, where I take Vj times Vj, which is 1. So the only remaining part here on the right hand side is again lambda j. And this is already what we wanted to show, namely that these coefficients lambda at the position j is exactly given by just Vj dot product u. So this here is the formula we wanted to show, namely this is j goes from 1 to m, Vj dot product u, so this is a number times the vector Vj. And therefore the coordinate vector is exactly given by this, because the coordinate vector, the entries of this coordinate vector are the coefficients here in the linear combination of an element written in the basis B. And now the third statement, we want to consider the coordinate vector with respect to our orthonormal basis B. So let's give this a name. So this is an element in Rm, because we have m basis elements, and also the other element W. So u and W are in our subspace V, and this B is an orthonormal basis. So let's call this y1 up to ym. And now we want to see what is u dot product W. Well, if the coordinate vector of u is given by this vector here, this exactly means that u can be written as a linear combination x1 times v1 plus blah 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 xm vm dot product, and the w, the coordinate vector, is given by this. This means w can be written as a linear combination y1 v1 up to blah 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 ym vm. And now we can multiply this here out, meaning I need to take a dot product of this with this plus the dot product of this with this, and so on. But now we can use again that these v are an orthonormal basis. So if I take here the dot product of this with this, so I mean this factor here I can always put outside, but the dot product here will be 1 if I take the dot product of v1 with v1. So the first term here is x1 y1 plus, and if I would take here x2 v2, the dot product with y1 v1, then because the dot product of y1 and y2 is 0, we don't get a term here. So the only terms appearing here are those when I multiply here the second term here with the second term here, the third term here with the third term here, and so on up to this term here. So in the end, I will just get exactly these numbers here. These x1, y1 plus the x2, y2 up to xm, ym. And this is exactly the dot product of these two coordinate vectors. And this is what we wanted to show, that the dot product, that the dot product of the coordinate vectors is the same as the dot product of these two vectors in the subspace. And this proves what we wanted to show. Okay, so yeah, I think this shows somehow that if you have an orthonormal basis, it's quite nice to work with, because I mean, if you have an arbitrary basis and I ask you, and I give you an element and I ask you for the coordinate vector, you always need to solve a linear equation. But here in this case, you see, you don't need to solve a linear equation. You just need to calculate these dot products. Yeah. And also here, you also, to check that vectors are linearly independent, if you know that they are orthonormal, then you don't need to then you automatically know that they are linearly independent, and you also don't need to solve a linear equation. Okay, so now we come to another important notation, namely to the so-called orthogonal complement of a subspace. So if I have a subspace U, then we can define the orthogonal complement of U in Rn. And the notation is that we take the subspace U, and then this symbol here, the symbol for perpendicular or orthogonal, and the definition is that this is a set of all vectors in Rn which are orthogonal to all vectors in the subspace U. So yeah, so all x such that the dot product of x with all elements in U is 0. So for example, if I have a line, so if this is my subspace U, what is the orthogonal? I mean, first, we learned a line through the origin is a subspace in R2, and the orthogonal complement of this subspace U here in R2 is exactly this line here, because on this line, make it straight. Stupid. Anyway, let's say this is a straight line. Then this here is the orthogonal complement. And if I have a plane, then the orthogonal complement of the plane would be the line, which is also the subspace, which is orthogonal to this. And if I just have a line in 3 dimensions, then the orthogonal complement would be a plane. And yeah, and the first, and so by definition, well, what I just said is that these examples I gave here, they are also subspaces, and this is one of the first statements here in this lemma, namely that if I have a subspace, maybe let's make this, if I have a subspace U, then the orthogonal complement is also a subspace. Then the second statement, the only element which is in U and in its orthogonal complement is just the zero vector. So like you can see in this example, for example here, the intersection of these two spaces is just the zero vector. And, and then if I have a basis of a subspace U and I have an element X, then these two statements are equivalent. So to be in the orthogonal complement of U is equivalent to being orthogonal to just the basis vectors. So this statement here seems to be stronger, because if you are an element in the orthogonal complement of a subspace, this means you are orthogonal to all elements in the space. And the statement on the right hand side here is that you're just orthogonal to the basis elements. And the statement of this here is that this is already enough. If you can show that an element is just orthogonal to these R vectors, so this is a subspace of dimension R, then you already showed that this is orthogonal to every vector in the subspace U. So in general, you don't need to check infinitely many conditions. So if you look at the definition here, the orthogonal complement is a set of all vectors which satisfies these conditions for all elements in U, and usually U contains infinitely many elements, but you don't need to check these infinitely many conditions. You just need to check that this is the case for the basis elements. And then a really important property is this one here. So if I have a subspace U and I have an orthonormal basis of the subspace U, then, oh, here's a typo, this should be Rn. So here I have a subspace in R. Oh well, here we know U is in a subspace of Rn. So if I have a subspace in Rn and I have an orthonormal basis, and now I take any element in Rn, so it doesn't need to be in U, it can be any element, then I can write this X as a sum of two elements, X parallel and X orthogonal or X perpendicular, where this parallel element here is an element in U. So this here is in U, and this here is in the orthogonal complement of U. And more precisely, this element in U is given by this thing here. So this is a linear combination of these basis elements, where the coefficients are given by the dot product of this X with the corresponding basis element. And well, this here is then just X minus this part here. And the non-trivial statement here is, or the thing we need to show, is that this is an element in U transpose. Because otherwise, if I define this to be anything in U, and I define this here to be X minus this thing here, then of course this statement here is true. But the important point here is that this element here is in the orthogonal complement, and this element here is in U. And we will also see later that these are actually unique. So for an element X in Rn, I can find unique elements in U and in U orthogonal, such that X can be written like this. Okay, so let's prove this lemma. So first we want to check that the orthogonal complement is a subspace, and well, this is actually quite boring to prove. So to check that something's a subspace, we can either show these three conditions, that 0 is in there, but why is 0 in there? Well, because the dot product of 0 with anything is always 0. So the 0 vector is orthogonal to any vector. In particular, it's orthogonal to all vectors in U. So therefore, the 0 vector is in U transpose. So this would be the first condition. If I have two elements, U and V, in, let's say x and y, if I have two elements x and y in the orthogonal complement, I want to check that the sum of these two is in the orthogonal complement. So if x and y are in the orthogonal complement, this means that they are orthogonal to any element in U. But if I take the sum of these two and I consider the dot product with U, then we can again use this rule here that I can write this out as dot product of x with U, dot product of y with U. And then I know, because they are orthogonal to any element in U, this here and this is 0. So this here is also 0. And therefore, x plus y is also in the orthogonal complement. And similar, if I take some scalar multiple of x and take the dot product with an arbitrary element in U, then I can use this rule here that scalars I can always put outside of this dot product. And again, here this is 0 because x is in the orthogonal complement, and therefore this is also 0. And therefore lambda times x is also in the orthogonal complement. So this shows these three conditions, and therefore the orthogonal complement of U is a subspace. And maybe as an extra exercise, you can try to think of maybe a linear map such that this here is the kernel of this linear map, and then this would also show that this is a subspace. And number 2, so what is number 2? The statement in number 2 is that the only element which is in the subspace U and in its orthogonal complement is just the 0 vector. And this is also easy to see, because let's assume I have an element x which is in U and in U orthogonal. This means because x is in U orthogonal and in U, this means that x is orthogonal to any element in U, but because it's also in U itself, this means it's orthogonal to itself. So this means that the dot product of x with x needs to be 0. And what is the dot product of x with itself? Well, this is just the sum of the squares of the entries of x. And if this is 0, this can just happen if all of these entries are 0, because otherwise I would add positive numbers here. And this just shows that, that x needs to be the 0 vector. And therefore any element in the union, in the intersection of U and U orthogonal is just the 0 vector. Okay, and number 3. So we want to show that these two statements are equivalent. So if I have a basis, then for an arbitrary element in Rn, being in the orthogonal complement is equivalent to being orthogonal to the basis elements. So in this direction here is clear, because if it's in the orthogonal complement, it's orthogonal to every element in U. So in particular, it's orthogonal to the basis vector of U. So we just need to show this direction here. So we want to show this direction here. So maybe here clear. So if I have an element in U, then I can write this element as a linear combination of these basis vector, which are now called U. And we want to show that if an element X is orthogonal to these, then it's already orthogonal to this arbitrary element in U. So we need to consider what is the dot product of X with W? Well, it's the dot product of X with this expression here, because the U are a basis, and therefore I can write any W as a linear combination of these U's. But then again, I use the same calculation as before. This is lambda 1 times X dot product with U up to lambda m times X dot product with UM. And because we assume that X is orthogonal to the basis elements, each of these terms are 0, and therefore this whole expression is also 0. And therefore, if X is orthogonal just to the basis elements, then it's already orthogonal to any element in the subspace U, because this W was now an arbitrary element, and any arbitrary element can be written as a linear combination like this. But then we can see that if we take the dot product of X with W, and if X is orthogonal to the U's, then it's already orthogonal to W. And therefore, this direction here is proven. And now to number 4. So we now have an orthonormal basis, and we want to show that X can be written like this. But the only thing we need to show is that this part here, that so clearly this is an element in U, because it's just defined as the sum of elements in the basis. Alright, so first clear is that this here, maybe let me write like this, clear, the statement which is clear is that this is an element in U. So what we want to show is that want that this element here is in U orthogonal. So what is this? It was defined as X minus X parallel. So X parallel was given by the sum here. I goes from 1 to R, and here I take the dot product of this X with the basis elements Fi, like this. So this is a definition of this X orthogonal. It's the vector X minus this linear combination. And we want to show that this is orthogonal to, that this is in the orthogonal complement of U. And to show that something is in the orthogonal complement is, we just need to check if it's orthogonal to the basis elements. Because this is what we just proved. If something is orthogonal to the basis elements, then it's already in the orthogonal complement. So we want to check if this vector here is orthogonal to the basis elements. So we need to check for all basis elements that if I take the dot product of some basis element Fj with the X orthogonal, that this is 0. And by definition, this is the dot product of this thing here, right? So if you write this out, it's Fj dot product with X minus and Fj dot product with this sum here. And now we use that these fj are an orthonormal basis. So if I multiply, I mean this here is just a number, so if you take the dot product of this with this vector here, you can again just put the number always in front. So here you will take the dot product of fj with these fi's, and because they are orthogonal, they are orthonormal, this dot product will always be 0, except for the case when this I equals j. And in this case, this fj times fj will be 1, because the dot product is 1, and therefore the only term we have left here is x dot product with fj. So therefore we get fj here in front, minus the only surviving term here, which is x dot product fj. And this is 0 because we learned that the dot product is commutative, meaning that this is the same as this. And this proved what we wanted to show. So again, if I have a subspace U and I have an orthonormal basis, then I can create an element in U by this sum here. So I take this arbitrary element x and take the dot product with these basis elements. This gives a number for each basis element, and this number I multiply with the basis element. This gives a linear combination of basis elements, therefore an element in U. And then if I subtract this element from x, then this will be something orthogonal. So let me draw a picture here. If I have a subspace U and I have some x, then this x parallel, this will be an element in U. So this vector here, different color, pink isn't good. So this here is x parallel, and I will get, if I take x minus x parallel, which is this vector here, then this will be an element in a U orthogonal. So this here is x orthogonal. Yeah, so this is something similar as we did with this orthogonal projection, but in this case, so recall this, if U, let's say if U is just the span of a vector U, then we defined this PU, which did exactly this here. And in the construction of this PU, we draw a similar diagram. But now we consider an arbitrary subspace U. So this U, for example, could be a plane. And now if I have the plane and some arbitrary vector in this space, then this x parallel will be the projection onto this plane, and this x parallel will be a vector which is orthogonal to the plane, and the sum of these two vectors will give back my original x. So here this x is the sum of the purple plus the blue vector. Okay. And you also see that the formula, if I have this orthonormal basis, then actually the formula for this purple vector here is extremely simple, because I just need to calculate the dot product of this x with the basis vector. And if you recall this orthogonal projection PU, this is quite similar to what we did there. So if U, capital U, is just the span of some small u, and let's say this has length 1, then this would be an orthonormal basis of U. And then if you look at the formula for PU, which we calculated, then we also just took the dot product of x with U times the vector U. And if U was not a unit vector, then we also needed to divide by the norm of U. But if U is an orthonormal basis, then this vector here is already 1 and we don't need to divide it out. Okay, so I hope I convinced you that orthonormal bases are really nice. So then we can now go to this algorithm which helps us to create orthonormal bases for our favorite subspaces. So, and this is called, after these two guys here, so this is called the Gram-Schmidt algorithm, or often you can find it as a Gram-Schmidt process. And what this algorithm does is, if we have a subspace V with an arbitrary basis, then it gives an explicit way to construct a new basis of the subspace V, which is an orthonormal basis. And the basic idea will be, so let's say I have so let's say this is R3. And now let's say I have two vectors B1 and B2. So they span a plane. And in this case, this is not an orthonormal basis because here they are not orthogonal to each other. But the idea will be that to create a new basis, we will start with the first basis vector B1. And because we want an orthonormal basis, we want to have that all of them have length 1. So the first basis vector will be the same vector as B1, but we normalize it to length 1. So this will be F1. And the second basis vector will be given by taking the second or original basis vector and project it onto this B1. So then by this, what we just discussed, we get some parallel vector here. And so the first step will be we will get some W2, which will be the this, maybe just, oops. So this will be the thing we just discussed, so we can say we consider the subspace spanned by just this basis vector B, or F in this case, and then we take this projection with the formula as before, and then we want to make it to length 1 again, so we normalize this new vector, and then maybe this, so I want to have these purple things both have length 1, and this will be our F2. And then we will see that these two vectors, they span the same plane as before, but now we will have an orthonormal basis. And this will be the basic idea of this algorithm. And to make this clearer, we will start, of course, with one example. So, so we will start with these three vectors, B1, B2, and B3. And they form a basis of R3. And what we want to construct now is a new basis of R3, which is an orthonormal basis. And, well, of course, you could say, well, R3, I can always take the standard basis as an orthonormal basis, but we want to demonstrate the algorithm here. And in general, this algorithm will be used for some subspace, and the standard basis will not be a basis for an arbitrary subspace. Okay, so let's start with the first step. So, as said before, we want to first construct F1. And this will be step 1. And as I said, the F1 will be basically just given by a B1, but we want that they have length 1 in the end. And then recall this notation from the beginning. This hat means we normalize this B1 by dividing by its norm. So F1 is always quite easy. It's just the first vector here, but we shorten or make it longer such that it has length 1. And now, so what is this in this case here? So what is the norm of B1? Well, we need to take the square root of the dot product of B1 with itself. So the dot product is 1 plus 1 plus 1, so it's 3. And therefore the norm is the square root of 3. And the vector is 1, 1, 1. So this will be our F1. And now, step 2. Well, now we want to construct F2. But of course, we cannot just take B2 and normalize it, because, well, then we would have two vectors which have length 1. But we want that they are orthogonal to each other. So, so what we want to do is first, so maybe after, let's say after the first step, we define U1 to be the span of just F1. Well, because F1 is just a multiple of B1, this is the same as the span of B1. So this is now a subspace. And we just learned that if I have a subspace and I have an arbitrary vector, then I can find a parallel vector to this subspace. So U1 is a subspace, which in this case is just a line in R3. And by this lemma, 12.5, the last statement, number 4. So let me go back here. If I have a subspace with an orthonormal basis, then for an arbitrary element here, so this will be now our B2, and here the orthonormal basis will be just given by our F1. So for this B2, we can now find a parallel part and an orthogonal part. And what we want to take is this orthogonal part here, which is given by B2 minus this sum here. So in this case here, so the statement is B2 can be written as B2 parallel. So this will be an element in U1 plus B2 orthogonal. So this here is in U1 orthogonal, meaning in this case it's just orthogonal to F1. And this is just yeah, sorry. So this here, by this formula, is just B2, the dot product with F1 times F1. So what we want is, we want this orthogonal vector here, which we will call a W, W2. So we will just say this will be the orthogonal vector, and this will be B2, this here, minus this parallel part, minus B2 dot product F1, F1. So what is B2? B2 is 1, 0, 2, minus, what is the dot product of B2 with F1? So we need to take the dot product of this vector with this vector. This will be, well, I will write it out. B2 dot product F1 is, so I have this 1 over square root of 3, and here I have 1, 0, 2 dot product with 1, 1, 1. So this is 1 over square root of 3. And here 1 times 1 plus 2 times 1, which is 3. And yeah, so this is this term here. And now this we want to multiply with F1. So this number here we want to multiply with F1. So we see here this 1 over square root, we get 1 over 3, and then this 3 cancels out. So this here is just 1, 1, 1. And if we subtract this, we get 0, minus 1, 1. And this is what we call W2. And this first the statement is, so this here is just this orthogonal part here. So the statement is that this is orthogonal to f1, which is the case because if I take the dot product of this here with f1, then this is 0. But we want also make it length 1. So our final f2 will be to take this w2 and normalize it. So we want to divide by the norm of this, which in this case is just the square root of 2. Yeah. So this is our f2. And now, so we have now f1 and f2, and this will give us a new space u2, which we say is the span of f1 and f2. Well, but we know that f1 is just a multiple of b1, so we can replace it there, and f2 is just a multiple of this w2, but w2 is a linear combination of b2 and f1. Therefore, because f1 is also just a multiple of b1, we see that this vector here is also in the span of b2 and b1. So therefore here this f2, if I take the span of f1 and f2, this is the same as the span of b1 and b2. Yeah. So I mean the main point is that in each step we will create an f, and we will create a subspace which is given by the span of the f's we have so far. But we want also make sure that this is still the same as the span of the b's we have. Because in the end we want that the span of all the f's is the same still as the span of all the b's. Because otherwise this wouldn't span the same space, and it couldn't be a basis of this space. Okay. And now we have f2, so in step 3, surprise, we want to calculate f3, and we do the same game as before. We say we have a subspace u2, and for any subspace and for any vector we can find an orthogonal and a parallel part of this vector in this space and an orthogonal part. So b3 can again be written as a b3 parallel, which is in u2, plus b3 orthogonal, which is in u2 orthogonal. And we define w3 to be just this part here, which is b3 minus b3 parallel. But we have an orthonormal basis of u2 given by this f1 and f2, so they span the space and they are orthogonal, so they are linearly independent, and therefore they form an orthonormal basis of u2. And if we have an orthonormal basis of a subspace, then the formula for this thing here is just given by the sum. So here I can take just the sum of b3, the dot product with f1 times f1 minus b3 dot product of f2 times f2. Yeah, and this thing here will be orthogonal to f1 and f2 because this is an element in the orthogonal complement of the subspace u2. So let's calculate this. What is b3? B3 is minus 1, 2, 1. So minus 1, 2, 1 minus, and maybe this I will just give you now, but if these numbers I get here confuse you, then either cry or check that this works, or ask me in the tutorial. So what you should get is 2/3 1, 1, 1 plus 1/2, 0 minus 1, 1. And in the end, this gives 5/6 times minus 2, 1, 1. Okay, so this is the W3, which is just the orthogonal part here of this B3. So this is an element in the orthogonal complement of this guy here. So this vector here should be orthogonal to F1 and F2. Indeed, if you check, if you take the dot product of this with the vector F1, which is basically this one here, you will see this is 0. And if you take the dot product of this with F2, which is basically this one here, then you also see that this is 0. But this is not our F3 yet, because it's still too long. So we want F3 to be, again, the normalized version of this. So we just shorten this, so this doesn't change the direction. So after making it to length 1, it will still be orthogonal to F1 and F2. And now, a stupid trick to normalize this. Well, you could also just put this inside here and then take the sum of the squares and take the square root. But normalizing a vector just means you want a vector in the same direction with length 1. So actually this number here you can completely forget and just think about this vector here. And the norm of this vector here is 4 plus 1 plus 1 is 6. So the square root of 6. So this here is 1 over the square root of 6 minus 2, 1, 1. And this is our F3. And then we define our U3 to be the span of F1, F2, F3. And then we already saw that the span of F1 and F2 is the same as the span of B1 and B2. But now F3 is this W3 here. But W3 is the linear combination of F1 and F2. So this here is in the span of B1 and B2. So therefore I can also write this F3 here as a linear combination of B1, B2 and B3. Or I can also write B3, if I put this here on the other side, as a linear combination as B1, B2 and F1, F2 and F3. So the statement is just that this is again the same as the span B1, B2, B3. And actually in this case, this was what we started with, this was R3. Or in general, this will be the subspace we started with. So this here, F1 was this. So this is F1. F2 was this. Stupid. Is this. And F3 is this guy here. This is an orthonormal basis of, well, in this case, R3. Yeah, and I hope this made clear how this algorithm works. So let me explain this now in general, but not so detailed. So the general idea is that of this Gram-Schmidt algorithm or process, if I have an arbitrary basis of some subspace U, then the goal is to find a basis, an orthonormal basis of this subspace U. So this here has dimension m, so there will be m steps, and the first step is always the F1 to just say this is the first basis vector, but normalized. Then we can define U1 to be the span of F1. And then in the next step, so let's take this step 2, then we have constructed F1, and then we take b2 minus b2 here. So this is what we didn't, I mean this part here is what we wrote before as b, well, BL parallel, and or in general this here is what we called BL transpose. So in each step we will construct UL, which is the span of F1 up to FL, and then in the next step we will take the next basis vector BL plus 1 and consider the orthogonal part of to this this subspace before by using this formula here, and this will give a new vector WL, which is orthogonal to all F before, and then we can normalize it and then add it to our list, and we will get an orthonormal basis of a new subspace UL. And after m steps we will see, or in each step we see that the span of the first LF of F1 up to FL is always the span of B1 up to BL. So after m steps we will have a span of F1 up to Fm, which is exactly the span of B. And because all of these vectors are orthogonal, we learned by this nice lemma or proposition that they are automatically linearly independent and therefore they are a basis. And this is what this algorithm does. And this you do in homework 8 with an explicit example. And as a consequence of this algorithm, we get the following theorem. Where am I? Yes, so this one here. Namely, the statement is that every subspace of Rn has an orthonormal basis. And this is clear because we learned that every subspace, so proof, we learned every subspace has a basis, an arbitrary basis has a basis, which doesn't need to be orthonormal. But then, if we use this Gram-Schmidt algorithm, we can always get an orthonormal basis out of this arbitrary basis. And therefore every subspace has an orthonormal basis. And then another statement, which is quite similar to the lemma, is that if I have an arbitrary subspace, then for all x there exist unique x parallel and x orthogonal, such that x is can be written as the sum of these two. So this is similar to the last statement of the lemma, except in the lemma we assume we have an orthonormal basis, but thanks to this theorem we don't need to assume this anymore, because we now know that every subspace has a orthonormal basis. So the proof of the corollary, so the existence of these is this theorem 12.6. So this gives orthonormal basis of U, and then by lemma, I forgot the number, 12.5 I think, we get this x parallel and x orthogonal. And what we need to show is now that these are unique. So let's assume we have two different parallel and orthogonal parts. So let's assume we can write x as x parallel plus x orthogonal, or we can also write it as y parallel plus y orthogonal, where these parallel things are in U and these orthogonal parts are in U orthogonal. And then if I subtract y parallel here, and I subtract this from there, then I see that this here is the same. Yeah. And on the left hand side, I have a sum or a difference of two elements in U. And we learned that if I have two vectors in a subspace and I add them or I subtract them, then this is still in U. And here I have two elements in the subspace U parallel, so this here is in U parallel. So therefore, this thing here, which is equal to this thing, this is in U and in U parallel. But this means, this thing and also this thing, they are both in the intersection. But we learned by this one statement that the intersection is just the zero vector. And therefore both of them are 0, which is just equivalent to. So if this here is 0, then this just means that x parallel equals y parallel and x transpose equals y transpose. Not transpose, parallel. Orthogonal, sorry. So I cannot have two different ways of writing x as a sum of these elements in U or in U orthogonal. So therefore there exist unique things like this, which are given by the formula in lemma 12.5. And this we will consider next time in more detail, namely this if I have a subspace and an element x, then this parallel part here is called the orthogonal projection onto the subspace U, and this we will use for some real-life application, namely if you want, for example, do a polynomial interpolation, or if you want to find, if you have a linear system which you cannot solve, but you want to find the best possible solution of this linear system, and this will lead to the notion of least squares, and this has to do with this orthogonal projection. Because if I have a linear system, Ax equals b, so if b is not in the image of this A, then this linear system doesn't have a solution. So what you do is you take the orthogonal projection of b onto the image of A, and then you get a linear system which you can solve. And because you take the orthogonal projection, we will see that this is actually the best possible solution you can get for this non-solvable linear equation. Yeah, see you then.